Let's have some fun. In this lesson, I want to show you how to pop up a window and draw things on it. In an earlier lesson, we painted some words on the screen, but this time we're going to draw some pictures. These are going to be simple squares and rectangles, but we'll be able to cover the fundamentals for drawing stuff. This file contains two classes. The overall structure of the program is the same as it was when we were drawing text in a window. That is, the Draw Squares class extends the Frame class so it can create a window in which to display components. The main method does nothing more than create a Draw Squares object which creates the window. The constructor begins by enabling events so we'll be able to close the window. Then a squares object is constructed and added to the window. The pack method sizes everything, and the show method displays the window. Just as we did when we were displaying text, the squares class extends the canvas object, and the actual graphics are rendered inside the paint method. The graphics object has some methods that can be used to draw simple shapes, and draw rect is one of those methods. The first two numbers specify the X and the Y positions of the upper left-hand corner of the rectangle being displayed. The next value is the width of the rectangle, and the last value is the height of the rectangle. Now, in this example, the heights and widths are equal, so that means the program will draw squares. They're all different sizes, and the upper left-hand corners of them are positioned so they will appear inside one another. Notice that the squares class is not defined as public. That means it can be in a source file with a name that is something other than the name of the class, but it won't be possible to access the class from anything outside this directory. That's okay, though, because we only want to use it in another class inside this same file. Notice that the Draw Squares class is declared as public. That means it must be in a file named drawsquares.java, and we'll be able to access the class file from anywhere. This isn't strictly required when we're just going to execute its main method from inside the same directory like we're going to do, but it's a good policy to declare things public because we might want to use them from somewhere else later on. Also notice, the import statements for both classes can all be put at the top of the source file. That's because it's only the compiler that needs them, and it reads the source file and memorizes them when you compile the program. Then they're thrown away because they're not needed anymore. Anyway, all that's left to do is compile the program and run it. This command compiles both classes, and each class is stored in its own class file. If we had 20 different classes defined in the same source file, each one of them would have created its own class file when it was compiled. The names of the class files are important because that's how Java locates the classes that your program needs when it runs. And here we have the class file showing the 3 squares that your class draws when it runs. When we ran Draw Squares, it found that it needed the class named squares, so it looked in the current directory for the file named squares.class and found it. The programs described in this lesson use the methods of the graphics class to fill overlapping rectangular areas with color. You can draw lots of things into the same window, and whatever you draw last will appear on top of whatever you've drawn earlier. Knowing that makes it easy to have things overlap the way you want them to, like we're going to do here. This program is named Fill Squares. It's a frame that loads and displays a canvas component, which is named F-squares. You've probably noticed that I keep referring to classes that extend the canvas class as being components. That's because the canvas class extends the component class, and there are lots of components in Java. There are things like menus and push buttons and scroll bars and all sorts of displayable objects, and canvas is one of them. The F-squares class extends the canvas class. The constructor sets the size of the window to 200 by 200 pixels, and sets the default background color to something other than white. Notice that the paint method uses the method fillRect 3 times to render 3 color-filled squares in the window. A new color object is stored in the graphics object just before each square is filled, so each one is filled with a different color. Here's what happens when you compile and run the program. Oh, wait, before I do that, notice that this class is named F-squares instead of just squares like I named the one in the previous lesson. The reason for this is that the compiler is going to produce a file named fsquares.class. If I had named the class squares, it would have produced a file named squares.class, just like in the previous lesson, and this new class file would have overwritten the other one. You must be very careful not to have 2 classes with the same name in the same directory, and it's certainly possible to do that accidentally. This can cause a very confusing bug that seems to go away every time you recompile things. Chasing a bug like that is like a dog chasing his tail. You can see it, but you can't quite get it. Each square painted in the window is smaller than the one that was painted before it, so the smaller squares come out on top. The color selection could probably have been better, but I don't have any taste, so it doesn't matter to me. The background color, magenta, is the one that forms the frame color around the outside edge. The next square is yellow, then comes red, then at the center, the black square is painted on top and is the only one that is not partially obscured. Let's make a modification to this program so it uses rectangles instead of squares. It's easy to do because all we have to do is change some of the dimensions. To keep it simple, I just added 100 to the height of everything. The window is 100 pixels taller, and each of the rectangles is 100 pixels taller than it was when it was a square. Other than that, everything was left exactly the same. When you compile and run it, it looks like this. This lesson is about drawing and filling circular shapes. Actually, the graphics class provides methods for ovals, but a circle is just an oval with the height and width equal to one another. The circles class extends canvas, and the paint method makes 3 calls to the draw oval method of the graphics object. The arguments passed to draw oval are just like the ones we use for draw rect. The way the draw oval method works is for your program to specify a rectangle, and an oval is drawn that exactly fits inside that rectangle. In this example, the rectangles specified are the same size and in the same position as the 4 squares that we drew a couple of lessons back, but this time circles are drawn instead. In this example, the first call to draw oval specifies the square with its upper left-hand corner about here, and its edges go here, and the circle is drawn that just touches the 4 sides here, 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 and here. This example happens to be placing circles in squares, but if the squares were rectangles, the circles would turn into ovals or ellipses. Let's look at an example of filling ellipses in different colors. In this example, the fill oval method is called 3 times, and the set color method is called once before each fill oval method, so each one is filled with a different color. All 3 of these overlapping ovals are the same distance from the left side of the window, and they all have the same width. The first oval, the yellow one, begins at the very top of the window and its height is the same as that of the entire window. The other two ovals are the same width as the yellow one, but their height is less, and they start further down from the top. You can use the draw and fill methods together to outline the figures. Now this is the same set of calls to fill oval as we had in the previous example, except some calls to draw oval have been added. The calls to draw oval are used to outline the filled area by being called with the same dimensions after setting the new color in the graphics object. Here the color is set to yellow, and we fill an oval with the yellow color. Then we set the color to black, and then we draw a black outline around the filled oval. The result is that after each oval is filled, it is immediately outlined in another color. I did a couple of them in black, and the last one in white so that all show up. The results look like this. The graphics object has methods for drawing and filling a rectangle with rounded corners. You draw it the same way as you draw a normal rectangle, except you add instructions to tell it how much to round off the corners. This program draws 3 rounded rectangles. The first 4 values you specify are the same as the ones you would specify to draw a regular rectangle. This rectangle has its upper left-hand corner 20 pixels from the side and from the top. It's square because the height and width are both at 160 pixels. These 2 extra values at the end specify the amount of roundedness that is to be applied to each corner. The first number specifies that a curve on the horizontal line should start 10 pixels back from the corner, and the second one specifies that a curve should start 10 pixels above or below each corner. This example draws 3 rounded rectangle shapes. Here's what it looks like. Each corner appears as a quarter of a circle. The circles on the corners of all 3 of these examples have radiuses of 10 pixels. Other than the rounded corners, the setup to draw a rounded rectangle is just like a regular rectangle. You can use different curvature for vertical and horizontal components, and you can fill the entire region with color. You might notice something different here in the import statements. Instead of listing each AWT class separately, I just used an asterisk. That way I can refer to class names such as color and canvas, and the compiler will look in the AWT package to find them. Also notice that the window event class still has to be imported specifically. The asterisk does not instruct the compiler to search through the sub-packages. By the way, the letters AWT stand for Abstract Windowing Toolkit. It's the collection of classes that do windowing and graphics in such a way they're system independent. That is, if you do some AWT graphics on Windows, your program will run and do exactly the same thing on a Macintosh or any other system that runs Java. The F-rounded class sets the background to light gray, then paints a blue rounded rectangle into it. This rectangle is square, just like in the previous example, but it doesn't have parts of circles in the corners. It has parts of ellipses. Let me run the program and show you what this looks like. Notice that the curvature in the horizontal direction begins 30 pixels from the corner, while the curvature in the vertical direction begins 50 pixels from the corner. The slight curvature in the corner gives you a shape that comes in handy for making quick graphic designs. Remember, I don't have any taste, but I will try to show you what I mean. Here again, the asterisk is used on the import statement and means that we can use names of classes such as font and font metrics without any further qualifications. This works okay as long as you don't happen to name one of your classes the same name as something else in the AWT package. Then you have a naming conflict and the results are sometimes entirely unexpected. Because of this, some people consider the asterisk to be a bad programming practice, but that's for you to decide. I use the asterisk, but not that often, because I rather like the idea of having all the classes I use listed at the top of the program. This program draws a signpost and writes a word on it. The post is drawn in black, and we draw it first so we can put other stuff on top of it. The sign is a rounded rectangle filled in yellow. A large, bold font is selected for the text. We get a font metrics object so we can measure the text and try to place it in the center of the rounded rectangle. Once the position of the text is determined, the string is then drawn in the middle of the rounded rect. Well, the vertical centering of the text is off just a bit. It was assumed that since the chosen text had no descenders, the text ascent value was the only thing that was needed to be considered as the height. But as you can see, that didn't quite get it dead center. As usual, the exact positioning of text depends a lot on the font, so you usually have to fill in arcs. An arc can be part of a circle or it can be part of an ellipse. Just like the earlier methods that were used to draw and fill ovals, the methods to draw and fill arcs require that you specify a box that the arcs are to fit in. But then you have to specify where the arc will start and stop inside the box. Here's an example. The first four parameters for the methods that draw arcs work just like the first four parameters to the methods that draw ovals. That is, they specify the upper left-hand corner and the height and width of a box in which the arc is to be drawn. The arc is inscribed inside this box just as if it were an oval, but these last two parameters are used to tell it exactly how much of the oval is to be drawn and how much is to be left out. Now, these numbers specify the starting and stopping points. The numbers are in degrees, and they range from 0 to 360 for a full circle. They're based on the Cartesian coordinate system. That's the one we all used in algebra in school. That means that 0 degrees is straight off to the right, and the rotation proceeds counterclockwise. 90 degrees is straight up, 180 degrees to the left, and 270 degrees is straight down. Let me show you how this example works. There are three arcs involved here. The outer arc goes from 0 degrees to 90 degrees here. The next arc begins at 0 degrees also and continues for 180 degrees here. The smallest of the three begins at the top, that is at 90 degrees, and continues from there for 270 degrees, and so it winds up back at the starting point. That's the 360 degree point. That is, the second value you specify is the angular distance from the first location, not the distance from the origin. Now, if you want, you can have the starting and stopping degree values greater than 360. Java will just continue around the circle however many times it needs until it gets there. The 360 degree one is a complete revolution. 720 degrees is 2 complete revolutions, and so on. Just like ovals and rectangles, it's possible to fill arcs with solid colors. The arcs are very much like the ones in the previous example, but these will be filled with color and look sort of like slices of pie. The first pie, the pink one, starts at 0 degrees and continues for 90 degrees. That's from here to here. The second pie, the red one, begins at 45 degrees and continues for 180 degrees. That brings it from here to here. The smallest arc is the black one. It begins at 90 degrees and continues for a full 270 degrees, bringing us back to the starting point at 360. And just like the earlier examples, arcs don't have to be drawn and filled inside squares. Now this example is just like the previous one, except the width of the window and the width of the boxes containing the arcs have all been extended by 200 pixels. You don't have to use one of the predefined shapes. You can construct a shape of your own by specifying a series of X and Y positions and calling the methods that join the dots. A shape like this, one that can be irregular and has a number of sides, is known as a polygon. The points that define the polygon, also known as the vertices of the polygon, are kept in a pair of arrays. These arrays are declared with 6 initial values each, so the Java compiler takes the extra step of creating actual arrays holding the values. Also notice that the arrays are declared inside the class but outside of any method, which makes them accessible to all methods of the class, and they are declared as private, which means they cannot be accessed by anything outside the class. Anyway, one array contains the X values, the other the Y values of each point in the polygon. This method is called with the 2 arrays, and a third value that specifies the number of points in the array to be used as the polygon. Actually, there could be more than this number of points in the arrays, but the method will only use as many as you specify. Probably the best way to describe how the polygon is drawn by this method is to show you. You may have noticed that the name of the file and the class is the same as the name of the method. But there's no possibility of confusion because Java is 100% picky about upper and lower case. This is the polygon defined by the members of the arrays. This location is the point 2020. The second point is here, the point 80, 180. Next, we come to here. X is 160, Y is 20. Then here, 320, 30. Then here, for 240, 180. And the final point is here at 380, 100. Now, this line is drawn from the last point back to the first one to close the polygon and complete the shape. Another method, not shown in this example, named draw polyline, works exactly the same way as draw polygon, except it doesn't draw this extra line to close the shape. In this example, I showed what happens when the shape overlaps itself. Java doesn't care. It just draws the lines from point to point until it gets to the end, and then draws this final line to close whatever shape's been defined. And just like with any of the other shapes, a polygon can be filled. Here we have the same pair of arrays as before, so the polygon we're going to be filling will also overlap itself. The paint method is also the same as before, except the call is made to fill polygon instead of draw polygon. Notice that in this example no colors were set, so the default white background and black fill color will be used. The shape of the polygon is exactly the same, and all the interior areas are filled. Now the polygon can overlap itself any number of times, and it can have filled areas overlapping one another, and all the enclosed regions will be filled. Notice how the lines have crossed each other here and here, where there are no vertices. But the software of the graphics object figured out they were there and used the results of that observation to determine the enclosed areas. A very special figure drawing method draws a beveled edged frame around a rectangular shape. But there's a little trick to doing it so it'll show up right. The beveled frame it draws is only 1 pixel thick, so it's a bit hard to see unless you do something to thicken it. Now this program draws rectangles with 2 types of beveled edges. The first thing we do in the paint method is set the value of colors stored in the graphics object to a nice neutral gray. It's best to use something in the middle of the color range because we're going to create a frame that's slightly darker and lighter than the selected color. The primary colors of red, green, and so on don't do so well when you start shading them. Once you see how this program works, try them and you'll see what I mean. The values of X, Y, width, and height are set to define the rectangle that's going to be framed. We use these values to call fillRect to fill an area with our basic color. Then, to make the frame thick enough to be seen clearly, a for loop is set up to loop 5 times. Each time through the loop, a call is made to draw 3D rect to draw a frame around the rectangle. Notice this last argument, the Boolean value. This tells draw 3D rect to shade the edges so the rectangle will appear to be raised. Once the 3D rectangle is drawn, the values for drawing it are adjusted so the next frame is drawn just outside the one that was just finished. The values of X and Y have 1 subtracted from them to place the new upper left-hand corner 1 pixel up and 1 pixel to the left of the current position. 2 is added to both the width and the height so the new frame line will fit just outside the one previously drawn. The value of I is never used in the loop. It's just a counter to determine the pixel thickness of the frame. You can make this number smaller to produce a thinner frame, and you can make it larger to produce a thicker frame. A value of 5 makes what I think is a nice thickness to a frame without it being too ostentatious. But I don't have any taste, so that's probably wrong. Here we draw a second framed rectangle that's very much like the first one. The values are all initialized, so the new rectangle is the same size as the other, except it's in a different location and will show up under the first one in the window. And notice this. This time the Boolean value is set to false, so the frame is to be shaded in such a way that the rectangle is to appear sunken into the surface instead of raised. When we compile and run the program, it looks like this. Now, if these look like push buttons to you, you've got the right idea. This is a good a way as any to create push buttons, and I know of some places where this technique is used. Notice that we only specified 1 color for our beveled rectangle, but it looks for all the world like there are 3 colors. That's done using a couple of methods of the color object that produce slightly darker and slightly lighter versions of a color. I'll be showing you how to do that in the next lesson. But in the program we just looked at, the paint method seems to be a bit repetitive. The same code was included twice to draw the two rectangles. You can do that if you wish, but there is another approach that's probably cleaner and easier to work with. This program does exactly the same thing as the previous one, except for two things. For one thing, it uses different colors, and for the other, it uses an internal method named draw bevel. This new method contains the call to draw 3D rect and the loop that contains it. The paint method now only sets the color and calls draw bevel twice with the appropriate values. It's in here that all the action takes place. First, a call is made to fill rect using the position, size, and color passed to this method as arguments. Notice that the graphics object is passed to this method because we can't draw anything without it. The loop is executed the same way it was before. If you'll remember, the only difference inside the bodies of the loops was the setting of the Boolean value passed as the last argument to draw 3D rect. In this case, the Boolean variable in-out is passed to determine whether our rectangle is going to be an innie or an outie. This window is the same as the previous one, except the colors are different. In this example, the color is set to magenta, which has the RGB values 255, 255, and 0. With two of the values already at maximum and the other at its minimum, there's no real way to create a slightly darker or a slightly lighter version without changing the color. Colors are never easy to work with. You just have to pick a starting point and experiment to see what happens. This lesson is about a special capability of the color object and also demonstrates another mechanism for creating loops in Java. The color class has methods that provide new colors that are darker or lighter versions of itself. This paint method fills a series of rectangles from left to right in the window, and each one is slightly darker in color than the one that came before it. Each rectangle is drawn so it covers half the height of the window and is 50 pixels wide. The purpose of this is for the program to draw a series of these rectangles side by side across the top half of the window. Here, the initial color is set to yellow. Notice the construction of this loop. The while statement will cause this block of code here to repeatedly execute as long as this value, x, is less than 300. With x initially set to 0, it'll certainly be true on the first pass. At the top of the loop, the color is set into the graphics object, so it'll be the one used to render the rectangle. The fill rect method paints the rectangle in the specified location. Now, the next rectangle should be to the right and adjacent to the current one, so the value of x is adjusted by the width of the rectangle that was just drawn. Here is where the color is changed. The existing color, which has its address stored in the reference named color, has a darker method that's called to produce a new color object. The address of the new color object is stored in the reference replacing the one that was already there. This program no longer contains a reference to the previous color object, so Java will destroy it and recycle it if necessary. The program has forgotten about it, but Java never forgets or loses anything. It's a very tidy housekeeper and will pick up behind you no matter how sloppy you decide to be. After the body of the loop is finished, if x is still less than 300, the loop executes again, and another rectangle is filled using a new color. This process continues until rectangles have been filled all the way across the window, each one in a color darker than the one that preceded it. The value of x is then reset to 0 to start over, and the value of y is adjusted, so the rectangles will now appear in the lower half of the window. The starting color for this loop is dark gray. The only difference inside the body of this loop and inside the body of the previous loop is that the color is set to brighter than the one that came before it. Here's what happens when we compile and run the program. As you can see, it doesn't take long for a color to reach its terminal condition. The yellow goes completely black after about 4 shades of becoming darker, and the dark gray color turns completely white after 4 shades of being set to brighter. These methods are not really meant to produce shading. They're meant to select darker and lighter colors to produce that beveled edge look on buttons. There's more than one way to produce gradual shades of color in Java, and we'll be looking into one possible approach in the next couple of lessons. Okay, it's your turn. You've been looking at my code and watching me type, but now it's your turn to do some programming of your own. I have 2 assignments for you based on the information and the lessons in this chapter. You'll be able to draw from the example programs that come with this chapter. Both assignments require that you create and display a simple window with graphics in it, so you can use just about any program from this entire chapter as your skeleton starting point. Just be sure to change all the names of things to the new names that you're going to use. Everything that you need to do the assignments can be found in the example programs you've already seen. Well, almost everything. There are a couple of things that will be new to you, but they're not difficult, and I mention them in some of the hints that I'll provide in just a few minutes. The assignments are simple, but you'll find that you have to twiddle with them a bit to make them work just exactly the way you would like. But there's nothing out of the ordinary there. It's just one of the fundamental laws of software that as soon as you finish writing a program, you have to make changes to it so it will do what you want it to do instead of what you told it to do. In the next lesson, I'll be showing you my solution to these problems, so you can cheat if you want to. But if you don't cheat, I'll guarantee you that your programs will be entirely different from the ones I wrote. No 2 programmers solve a problem the same way. There's nothing wrong with that. It's just the way things are. Any program can be written in thousands of different ways, and no 2 programmers ever think alike. If any program you've seen so far were implemented by 500 programmers, there would be 500 distinct versions of it. And this is not a bad thing. It's a good thing. You start by thinking the problem through. Well, part of the way through, anyway. Once you get your program written and working, you thoroughly understand how it works. If you were to use someone else's idea of the shape of the program, parts of it would always remain a mystery, and it would take you a lot longer to write the program. And you may not be able to ever get it to work. Just do your thing and see how it turns out. The first of the 2 problems is the checkerboard problem. Pop up a window that contains a 4x4 checkerboard pattern that completely fills the window. It's obviously made up of a collection of 16 rectangles in 2 different colors, positioned in such a way that the colors alternate. A simple checkerboard. Your first hint is that you should make the window square so the aspect ratio of all the rectangles it contains are also square, and the length of the sides of the window should be divisible by 4. That'll make it easier to place the start and stop side of each rectangle on a proper boundary. There are 2 fundamental approaches to this problem. You can either write the code to draw each square independently, or you can use looping to draw the squares. Either one is fine. That's up to you. Your second assignment is to paint a window that fades from one color to the next. The color should be at its darkest on one side of the window and smoothly fade to white before it reaches the other side. You already have almost everything you need to do this, and I'll be giving you a couple of hints here in a minute with the rest of the stuff you need. While fading from a color into white or into black is the easiest, it's also possible to fade from one color into any other color. If you prefer, you can fade to a color other than white. The only difference is the arithmetic you use to adjust the color values. Looping can't be avoided in this program. You'll have to establish a loop and create a new color object each time through it. You can make the rectangle as thin or as thick as you prefer, but thinner rectangles will make for a smoother color fade. You know that red, green, and blue values of the color object range from 0 to 255. The values 255, 255, 255 represent white. I mention this because in light, the presence of all colors is white, while in paint, the presence of all colors is black. But this is light, not paint. To be able to control the exact color values as you proceed from one to the next, you'll need to get access to the red, green, and blue values of the current color, change them slightly, and use the new values to create a new color object. You can extract the red, green, and blue values individually from a color object by using the three methods get red, get green, and get blue. If this is not entirely clear to you, take a look at the API documentation of the methods of the color class, and you'll find descriptions for these methods as well as other methods that retrieve color values. Well, that's it. As I said, I'll be showing you the solutions in the next lesson, but you should make a sincere effort to write your own version of these programs before you peek at my solutions. Even if you don't get yours working, attempting to get them working will make the solutions very easy for you to understand, since you dug around inside the problem yourself. The previous lesson posed a couple of programming problems, and this lesson provides possible solutions for them. Let me say again that there are thousands of programs that will satisfy the requirements of the assignments. These are just my way of doing it. All right, here's the checkerboard. My solution was to first create a window that's 256 by 256 pixels, which I was able to divide evenly into 16 rectangles that are 64 by 64 pixels each. To handle the situation of 4 across and 4 down, I nested one loop inside another. The outer loop executes 4 times, 1 for each column of the checkerboard. Each time the outer loop executes once, the inner loop executes 4 times, 1 for each row in the checkerboard. That means that this entire block of code is executed once for each square on the checkerboard. Take a look at this if statement. This is where I did something you could call sneaky. I decided to let the background color show through for half the squares, which meant I only had to paint the other half. This if statement determined whether or not this particular square was one that had to be painted. Now, the value of I goes from 0 to 3, and the value of j goes from 0 to 3. So I determined that if the sum of two numbers was an even number, that was a square that needed to be painted. For example, if I is 2 and j is 1, the sum of those two numbers is 3, which is an odd number, and that square does not need to be filled with black. So the next trick was to figure out whether this sum is odd or even. That's why I inserted the AND operator here. The AND operator looks at the bits and the numbers on each side of it and results in a value that is made of only the bits that are set to 1 that were set to 1 in the values of both numbers. Only odd numbers have the lowest order bit set, the 1 bit, so ANDing a number with 1 will result in 1 only if it's an odd number. If it is an even number, the result of the AND operation is 0, and the code to paint the square will be executed. If the number is odd, nothing else happens. The next job is to determine the values of x and y. Since each square is 64 pixels high and 64 pixels wide, it's simply a matter of multiplying the number of the square by 64 to find its position in the window. Once the location is known, a 64 by 64 rectangle is painted black. Now here's what happens when the program is compiled and run. And there it is. That's the 4x4 checkerboard. By just changing a few of the constants in the program, it could be modified to be any size and even made rectangular instead of square. The second half of the assignment was to create a window containing a shading of color from one side to the other. I did this by inventing my own color that had RGB values that provided me with plenty of room for change. The color fading appearance is achieved by filling a succession of rectangles, one beside the other, each one with a slightly different color. At the top of the paint method, the dimensions of each of the rectangles is set to the height of the entire window, but only 2 pixels wide. A color is defined using some RGB values that will be convenient to modify as we go. A loop is defined that will repeat itself until the value of X has reached the right side of the window. At the top of this loop, the set color method is called, and a rectangle is filled at the current position. The value of X is then adjusted by the width of the rectangle, getting ready to paint another one. The red, green, and blue values of the current color are extracted from the current color so we can adjust the settings and create a new color just one shade lighter. Each of the 3 primary color value settings has one added to it, checking to make sure it doesn't exceed the maximum valid value of 255. Here at the bottom, a new color is created and stored in the color reference, which means that the new color replaces the current color. At this point, the loop starts over, draws a rectangle with a new color, and makes the same adjustments all over again. If we were fading to some other color, something other than white, these numbers would be adjusted toward the corresponding values of the other color and not allowed to go beyond it. But that's an exercise that I'll leave to you. Here's what it looks like. As you can see, the color changes from its very dark original setting across the window to white. The rectangles, being only 2 pixels wide, make the color transition appear very smooth. It's impossible to see any rectangular edges because the color change in the neighboring rectangle is so slight.